So in this video, we're going to focus on how one can go about constructing two colorings of complete graphs in such a way as to give lower bounds for various two-color Ramsey numbers. Now, everything that we've done with Ramsey theory so far, we focused on coloring the edges, and then we're looking for an underlying subgraph of one of the two colors. To actually go through the construction that we're going to see today, we need to also introduce the concept of vertex colorings. So it can be a little confusing having both edge colorings and vertex colorings coming into play, but it's unavoidable with the theorem that we'll be discussing. So let's start out by defining what a vertex coloring is for a graph. If we have a graph G, then a vertex coloring is just going to be a function that goes from the vertex set of G into the set of numbers 1 up to some number t. And we're thinking of 1 up to t as representing our colors. It doesn't really matter what we call them. I can call them red, blue, green, and maybe t would be 3 in that case. Doesn't make any difference. We're just going to use numbers. And if we take any collection of vertices that all map to the same number, the set of all such vertices we refer to as a particular color class. Now we say that a vertex coloring is proper if no two adjacent vertices receive the same color. And another way of stating that is if we have the same image for two vertices v1 and v2, then the edge formed by v1 and v2 is not in the edge set of G. Of course, the minimum number of colors needed in order to properly vertex color a graph G, we refer to as the chromatic number. So hopefully this is a concept that you've seen before. We denote that as chi of G. And something you may not have seen before, but related to chi of G, is what we call the chromatic surplus of a graph. And so the idea is that suppose that our graph G has a chromatic number chi of G. If we take all proper vertex colorings that use chi of G colors, then we're going to let S of G denote the minimum number of vertices in any one of those color classes. And so in a little bit, I'll go over a theorem that's due to Burr that will actually make use of the chromatic surplus. But first, I'm going to put up a theorem that's due to Chvátal and Harary. They proved this theorem in 1972, and this will give us a lower bound. So let me pause it, and I'll put the theorem up. So beginning in the early 70s, Chvátal and Harary published a series of papers which they refer to as generalized Ramsey theory for graphs, but basically they're starting to consider graphs other than just complete graphs as the arguments of Ramsey numbers. And in the third paper that they published, this was in 1972, they included the following general construction. And so what it states is we're going to consider graphs G1 and G2, and we're going to let C of G1 be the number of vertices in a largest connected component of G1. Now, in particular, if G1 is connected, then it's just the order of G1. But if it's not connected, it's just the number of vertices in its largest connected component. Then we end up with this lower bound. The Ramsey number for G1, G2 is greater than or equal to C of G1 minus 1 times chi of G2 minus 1 plus 1. So let's go through and take a look at this construction. And so I started drawing the picture up here, but the idea is that we're going to begin by considering chi of G2 minus 1 copies of the complete graph K sub C of G1 minus 1. And we're going to color the edges within each one of those copies red. So let's go ahead and consider the disjoint union chi of G2 minus 1 copies of chi of C of G1 minus 1 whose edges are red. And so the way that I've drawn it, I mean, think of this as being a complete red K C of G1 minus 1. This is another one, another one, another one, and so forth. And the total number of copies we have is chi of G2 minus 1. Now, we don't have any edges interconnecting the copies yet. But what we're going to do is we're going to start drawing all possible edges interconnecting them as being blue edges. So interconnect copies of K of C of G1 minus 1 with blue edges. And so the way that I'm going to represent this, I'll just kind of draw some edges in between all of these. A lot of different possibilities here. Just assume every possible edge is drawn in between any vertex in one copy with the vertex in a different copy. Now, at this point, what we've created is a complete graph, a K sub C of G1 minus 1 times chi of G2 minus 1. So this gives a red-blue coloring of K sub C of G1 minus 1 chi of G2 minus 1. So now the claim, what we have to do to finish our proof is argue that we do not have any copies of red G1s and we do not have any blue copies of G2 anywhere in this picture. So let's focus first on the underlying red graph. Well, if you look at the underlying red subgraph in this picture, notice that we can't actually have a copy of G1 because a largest connected component of G1 requires C of G1 vertices. And the largest connected red component within this picture has C of G1 minus 1 vertices. So that prevents us from having a red G1 anywhere in here. So no red G1 exists. Since the largest red component only contains C of G1 minus 1 vertices. So it's not too hard to argue the lack of a red G1, but now we need to think about a blue G2. This gets a little bit more difficult. However, notice that every single blue edge connects one copy of one of these complete graphs with a different copy. So one way that we can go about forming a proper vertex coloring of any blue subgraph is to assign colors for the vertices based on which copy of these complete graphs the vertices are contained within. So this is where it gets a little confusing because we're coloring both edges and vertices, but now I'm going to give maybe all the vertices here color 1, all the vertices here color 2, color 3, color 4, and so forth. And at this point, we'll have properly vertex colored every blue subgraph because we don't have any blue edges entirely contained within one of these copies. And so the reason why that prevents us from having a blue G2 is having a blue G2 would require chi of G2 colors, but we're able to properly vertex color every blue subgraph using fewer colors than that. So that's the final argument. So let me erase this part of the proof and I'll finish putting that up. So we can properly vertex color every blue subgraph by assigning vertex colors according to the copies of K sub C of G1 minus 1 that the vertices lie within. Therefore, we're able to properly vertex color every blue subgraph using chi of G2 minus 1 colors. say using at most. Therefore, no blue G2 exists. So at this point, if we think about the Ramsey number R G1, G2, this is the smallest number P, such that no matter how you color with red and blue the edges of KP, you're guaranteed to either get a red copy of G1 or a blue copy of G2. But we've just produced a construction that lacks both of those monochromatic subgraphs. Therefore, if we were to look at the Ramsey number for G1, G2, that must be strictly greater than the number of vertices we have in this picture. And that number of vertices is C of G1 minus 1 by G2 minus 1. And that does it. If you want greater than or equal to, you just add 1 to the right-hand side, you get the result of the theorem. So that completes our proof. So let's think a little bit about one special case of choices of G1 and G2 that's kind of interesting to look at. Let's look at the case of a tree compared to a complete graph. So I'll keep the theorem up so we can look at it. So let's consider a tree TM. So we're going to let TM be a tree order M. So it's important to spell this out. Sometimes you'll see TM where M is the size of the tree, which is always 1 less than the order. But in this case, we're focusing on M being the order. And remember the definition of a tree, it's just a connected graph that's acyclic. There's also a lot of equivalent definitions, but that's really the main one that's usually given. So let TM be a tree of order M. Well, because it's connected, if we look at C of TM, well, it's connected, so we just get M back. It's just the order of that graph. At the same time, if I consider the chromatic number for, say, Kn, well, any complete graph, every single vertex must be colored differently from any other vertex because they're all adjacent to one another. So it requires whatever the order is to get a proper vertex coloring. So if we go ahead and apply this, we get that this is greater than or equal to minus 1 and minus 1 plus 1. Now, it took about 5 years, but this came out in 1972. 5 years later, Chvátal wrote a paper where he was able to show that not only is this a lower bound, it's also an upper bound. And that proof will actually be the focus of the next video that I make. But for now, this does turn out to be a quality. Whenever we get to that next video, we'll show that. Another interesting aspect of this result is that in 2011, Hook and Isaac proved not only that the construction we went through is this lower bound, that was known, but they proved that that is the only construction on one fewer number of vertices than what we have here that will avoid a red tree and a blue KN. And so basically they proved the uniqueness of what we call a critical coloring. And that observation led to them also defining what we refer to now as star critical numbers, star critical Ramsey numbers. And those will be the focus of a video that I'll record later on. So this is just one application, but the next thing I'd like for us to take a look at is an improvement on Chvátal and Harary's lower bound theorem. It's an improvement that was published in 1981 that's due to Burr. So let me pause the video and I'll put that result up. So 9 years after Chvátal and Harary's original lower bound, Burr came up with an improvement of it. And this is where we introduced the chromatic surplus that we defined earlier. And so we're going to assume that the chromatic surplus for G2 is less than or equal to C of G1. Remember, that's just the the maximum number of vertices contained within a largest connected component. And so to prove this bound, well, notice that the bound does incorporate the surplus here, and that's taking the place of where we had the +1 in Chvátal and Harary's theorem. And so we're going to go ahead and start with basically the exact same construction that we had before. So we're going to start with the same construction that was in the previous proof. Specifically, I have chi of G2 minus 1 copies of red case of G1 minus 1s, all interconnected with blue edges. Now what we're going to do next is we're going to add in one more copy of a red complete graph. But this time it's not going to have chi of G1 minus 1 vertices, it's going to have S of G2 minus 1 vertices. So when I say a red, I'm referring to the edges. So a red case of SG2 minus 1. Connected with blue edges to the rest of the graph. Let me go ahead and draw that into the picture. I'll put it off to the side here. So I have a chi S of G2 minus 1. I'm assuming that this is red. And then all the edges coming from vertices here to any other vertices up above, they're all blue. Now we have two separate cases to consider. So let's look at case 1. This is going to be the case where S of G2 is equal to 1. Well, if S of G2 is equal to 1, there's 0 vertices here. I'm really looking at the former construction. We already know what happens in that case. In fact, that gives us exactly the result that we had before, because we'd be plugging a 1 in here. We'd have Chvátal and Harary's lower bound. So this is the case we've already handled. So if S of G2 is equal to 1, and this is the case that we proved already. So really this is only going to be interesting if this is greater than 1. That's the only case where this is going to give us some larger number. Let's take a look at case 2. So if it's greater than 1, then we still are lacking a red copy of G1. And again, this comes down to looking at the number C of G1. That's the number of vertices in a largest connected component of G1. Well, this isn't big enough, this isn't big enough. None of these are big enough to contain that component of G1. This one's also not big enough because notice the assumption that goes into this theorem is that S of G2 is less than C of G1. So we have potentially fewer vertices here than we do in any one of these copies. So we still do not have enough to have that largest red component. So no red G1 exists, since no red component contains C of G1. But now we still have to make the argument about G2. Well, in the case of G2, we could still go through and color the vertices according to which one of these complete red subgraphs they lie in. But this time we actually do have the right number of colors for a proper vertex coloring. But anytime we include this set in the picture and we have our colors there, we can get our proper vertex coloring using chi of G2 colors. But notice that the chromatic surplus, remember that's the minimum number of vertices in any color class among all possible proper vertex colorings of your graph that contain chi of G2 colors, it's not big enough. And so whenever we do actually look at a case where we use the right number of colors to get that proper vertex coloring, we don't have enough vertices in our chromatic surplus to work. So that's sort of the idea behind why we're going to lack the blue copy of G2. So I'll just say again, we can properly vertex color vertices in blue subgraphs according to which red complete graphs they lie in. However, this produces a proper vertex coloring using chi of G2 colors with less than S of G2 colors or vertices in a color class. And that does it. Once again, we've managed to avoid having a red G1 or a blue G2. And so if we take this construction and we apply it to the Ramsey number, what we find in either case is that R of G1, G2 must be strictly greater than the number of vertices that we have here. So that number is given by the same number we had before plus S of G2 minus 1. So C of G1 minus 1, chi of G2 minus 1 plus S of G2 minus 1. And of course, if you add 1 to that, then we can write it as greater than or equal to, and that gives us the statement of our theorem. And so that's the end of this video of going over the lower bounds. What we'll be focused on in the next video is we'll take a result of Chvátal, and we'll show actually that the number that we get when we use a tree versus a complete graph is the actual Ramsey number.